roughly an hour.
Okay.
Yeah, take it away.
Great. Yeah, thank you for the invitation. It's always a pleasure to be in Berlin, albeit virtually. And yeah, as Julio said, I'm going to tell you about some work on the classification of mixed state topological orders. And this was done in collaboration with Meng Cheng. This is a very active field. There were a few papers with overlapping results that came out around the same time as ours. We're aware of some that are still to come out yet, but I will highlight this paper down here. And if at the end of this talk you're confused and nothing I said makes sense, there's still hope. I would recommend seeing this reference, as many of our results also appear in this work. This is a talk on topological phases of matter. We have a very solid understanding of topological orders in 2+1 dimensions. We know that they exhibit locally indistinguishable ground states when you put them on a manifold with non-trivial topology, and they exhibit quasi-particle excitations with exotic exchange statistics. These two properties make them especially promising for building a quantum memory and even doing quantum computations by moving around these quasi-particles. We also have a good understanding of their classification. There's a sophisticated mathematical theory known as modular tensor categories, which captures all of the possible topological orders that we could hope to realize. Intuitively, what modular tensor categories encode is the information about the properties of the anyons, or these quasi-particle excitations. What can you do with anyons? Well, you can fuse them, you can braid them by moving them around one another. All of that information and the consistent rules are captured by modular tensor categories. And at this point, we expect that this classification is complete. The proof is that we don't have any counterexamples, but we expect at least that modular tensor categories capture all the possibilities. There is an important caveat in this story, and that's that we make a very big assumption, an assumption that would make experimentalists somewhat queasy. We assume that the system is well isolated from the environment. We're studying the classification of topological orders in closed systems. To draw an analogy, that's kind of like studying cakes that look like this, just absolutely pristine. But in reality, experimentalists are working with something that looks more like this. And this isn't a knock against experimentalists. This is just to say that our assumptions in deriving this classification are somewhat unrealistic. So on the one hand, we've classified topological phases of matter in closed systems. On the other hand, experimentalists are having to deal with dissipation, disorder, and decoherence. And this isn't their fault. These things are inevitable. What do we want to do with the topological order? Well, ultimately, we might want to measure something, probe it, or use it to perform quantum computations. That involves interacting with the system. We are part of the environment, so that means that we need to allow the environment to interact with the system, and that'll lead to decoherence. So a priori, it seems like this picture on the right is, you can see my mouse, right? Oh, my computer decided now was a good time to update. Sorry.
I think we can't see your mouse.
How about now? Now you can see it?
Yeah.
Yeah, okay.
Perfect.
I had to settle some things with my computer first. Right, so what's fundamentally the difference between these pictures? Trying to study any specific instance or dissipation, disorder, and decoherence in general is tricky, but abstractly, what distinguishes these two pictures? Well, the system on the left is fully described by a pure state, which I've written here as a density matrix. This is a projector onto the state psi. Well, the system on the right is instead most accurately captured by a mixed state, a probability distribution of pure states. Intuitively, you can think of these indices I as labeling disorder realizations, or some configuration of errors. Pi tells you the probability of that error configuration, and psi I is the state with those errors applied. So the question we should be asking ourselves is, to what extent does our understanding of topological phases of matter in closed systems carry over to the setting of mixed states? And this is a question that has been asked before, especially in recent years. People have been interested in this question. Here's an incomplete, very proper subset of the papers on the subject just in the last few years. Although I will comment that many of these papers focus on the case of symmetry-protected topological order, and instead here I'll be interested in intrinsic topological order. Here's the plan. I'm going to start by defining pure state topological orders. I was told that pure state topological order is somewhat familiar to this audience, so this will be more about setting conventions, and I'll use as an example the toric code. Then I'll give a working definition for mixed state topological orders, and our example will again be the toric code, but now a noisy toric code. And this noisy toric code will focus on quite a bit because it captures many of the abstract features that can arise in the setting of mixed states. One possibility for mixed states is an incoherent proliferation of anyons. We'll construct a non-trivial example, and I'll generalize widely and claim to have a complete classification of mixed state topological orders. And I'll conclude by frantically running out of time, flipping through the last third of my slides, and then leaving open questions on the overhead. Despite that, please don't hesitate to ask questions, interrupt me if something's unclear. Naive questions are especially welcome. I have a feeling that people expect that they should understand mixed states and quantum channels just because it's talked about in intro quantum courses, but I got myself very confused about these things time and time again. So please don't hesitate to interrupt me if something's unclear. Okay, as promised, pure state topological orders. We're working with many body systems in a tensor product Hilbert space. This Hilbert space is huge and it has many states that are unphysical. So we need to restrict ourselves to a physical set of states to define pure state topological order. The first condition we'll impose is that we're only interested in states that appear as ground states of gapped local Hamiltonians. This is still too broad of a class of states. This includes GHZ states, this includes cat states, things that spontaneously break the symmetry. So to rule those out, because we don't really want to consider those as having topological order, we'll further only consider states that have short-range correlations, meaning specifically that for any local operators, OI and OJ, the connected correlator vanishes sufficiently fast in the separation between I and J. And this is a class of states that we'll consider. Now we'll, yeah, is there a question?
No, I don't think so.
Oh, okay, thanks. Yeah, now we'll impose an equivalence relation to define topological phases. We'll say states psi1 and psi2 are equivalent or belong to the same phase if there exists a quasi-local quantum circuit, that is the finite time evolution by a local Hamiltonian, which maps psi1 to psi2. Just because I don't know how to draw the finite time evolution of a local Hamiltonian, I'll just approximate that with a finite depth circuit. So here's an example where psi1 belongs to the same phase as psi2 because I can prepare psi2 by applying a finite depth circuit. This equivalence relation partitions the space of states into equivalence classes. We designate the equivalence class with the product state as the trivial phase, and all other phases are non-trivial topological orders. As I alluded to already, we expect to have a complete classification. These equivalence classes can be labeled by modular tensor categories. But there's a more modern perspective that I'd like to emphasize, and that's that in each of these phases, there's a spontaneously broken so-called generalized one-form symmetry. And to illustrate this, let me just focus on the toric code and show that the toric code spontaneously breaks a one-form symmetry. It's this idea that we'll use to generalize to mixed state topological orders.
I have a quick question on the equivalence relation. You say constant depth circuits. But I guess you're also allowed to get some auxiliary qubits and trace them out, stuff like this.
Not allowed to trace them out, but you're allowed to add auxiliary qubits. That's right.
Okay.
Yeah, that's implicit here. You can add ancilla, then apply a quasi-local quantum circuit.
I'm sorry, what does quasi-local mean in this context?
Yeah, I mean, it's like polylogarithmic depth in the system size. It's something like finite time evolution by a local Hamiltonian. That's what I mean.
Okay.
Yeah, thank you. So let's see an example. Just to set some conventions, I'll define the toric code on a square lattice with a qubit on every edge. The Hamiltonian is composed of two types of terms. There's the vertex term, which is a product of Pauli X operators around a vertex, and a plaquette term, which is a product of Pauli Z operators around a plaquette. These terms are mutually commuting, so they can be simultaneously diagonalized, and we can immediately write down the ground states, plural, of the toric code. Here's an example of a ground state. I've written this in the X basis, and I'll use this basis throughout the talk. What you're seeing here is a superposition of product states. Each of these is an X basis state. And the way I've labeled this is the bare edge corresponds to a plus state. So you should imagine there's a plus state on all these bare edges. The blue edges correspond to minus states. Why is this a ground state of the toric code? Well, the vertex term enforces that there are an even number of minus states incident on a vertex, while the plaquette term fluctuates the string configurations. So at the end of the day, a toric code ground state looks like an equal amplitude superposition of closed loop configurations. And as we know, if you put the system on a torus as it should be, then there's a fourfold degeneracy. So what I've drawn here is a torus. You should imagine these opposite edges are identified. So a single arrow is identified with a single arrow, double arrow is identified with double arrow. So you roll this up and it forms a torus. And I'll represent the state with an even number of strings wrapping around both the X and Y cycles of the torus by this empty torus ket. But there are other ground states, as you can imagine. We can wrap strings around non-contractible paths. This one has an odd number of strings wrapped around the y-axis. Here's one with an odd number of strings wrapped around the x-axis. And finally, we can have an odd number of strings wrapped around both the x and y-axes. The modern understanding of where this degeneracy comes from is from spontaneous symmetry breaking. The toric code has a one-form symmetry, which is spontaneously broken. And that explains this degeneracy on a torus. To make that more explicit, what are the one-form symmetries of the toric code? Here, by one-form symmetries, I'm talking about symmetries that are supported on one-dimensional submanifolds. There's a Z2 cross Z2 one-form symmetry of the toric code Hamiltonian. Here's what symmetry operators look like. This one's a product of Pauli X operators along a path in the dual lattice. This is generated, at least locally, by the vertex term. There's also a product of Pauli Z along a path in the direct lattice, which is generated by the plaquette term. On a torus, there are global generators. This looks like wrapping a string of X's or a string of Z's around the torus. Most interestingly, these global generators don't commute with each other. In high energy language, we say that this Z2 cross Z2 one-form symmetry has a mixed anomaly. And that's illustrated by the fact that these strings fail to commute with one another. One implication of the anti-commutivity here is that we cannot find a ground state that is symmetric under the full Z2 cross Z2 one-form symmetry. What has to happen? Well, it means that the ground states can't satisfy that symmetry and there's some spontaneous symmetry breaking. And we can see that explicitly by computing the connected correlator for some non-local order parameters. So here's an order parameter that we can use to detect the spontaneous symmetry breaking of the one-form symmetry in the toric code ground states. This is a Z string operator wrapped around the y-axis. This is charged under the Z2 symmetry in the sense that if I take this Z2 symmetry generated by X strings and conjugate my order parameter, the Z string operator, I get -1 times that string operator. So now let's compute the connected correlator using the Z string operator as an order parameter. And here it is. I've inserted a string at I and inserted a string at J. And here I am subtracting the product of the expectation values. These here are meant to be operators. These are operators. These are the Z string operators, and these are the states. So what do we get? Well, acting with these operators on the states, that inserts a string. These have, the overlap here is 1. These have difference in the string configurations. One has an odd number of strings, the other has even number of strings. So the overlap here will be 0. And in total, we find that the connected correlator is 1, independent of the separation of I and J. That tells us that this one-form symmetry has been spontaneously broken.
Do you need to do
We've now
that? Oh, sorry. Yeah.
Go ahead.
Do you need to do the calculation for every generating part of your homology group, like every non-trivial one, right?
You can. That's right. Yeah. So you could take, as another example, you could write down an X string operator that's charged under the Z string operator and around the X axis. And you could do the same computation there to see that the other Z2 symmetry is broken.
Okay, but my question was more if one follows from the other. No, thanks for answer. But if I know that in this case the Z string operator along one direction has this non-zero expectation value, is there some property that I can use in the definition of this of the ground states that from which I can directly infer that it also has to be like broken along the other line, along the orthogonal direction?
Yeah, that's a good question. I mean, what I can think of is you can rotate the toric code. There's some symmetry that leaves it invariant. You can also exchange E and M anion. So in that sense, yes. But in complete generality, I'm not sure how to argue that spontaneously breaking one of the Z2s automatically implies that you spontaneously break the other Z2. But it's a good question.
Okay, thanks.
Now, so this is at the fixed point. We can ask, well, what happens when we move away from the fixed point? It turns out there is still spontaneous symmetry breaking away from the exactly solvable toric code. So imagine we have a state psi prime, which also belongs to the toric code phase, meaning you can find some quasi-local quantum circuit that maps psi prime to psi. Then we can also map these one-form symmetry generators as follows. We just conjugate them by this unitary U. And the effect is it spreads out this operator, it fattens the string operator. But these are good symmetries of psi prime. So there's an emergent symmetry, there's an emergent Z2 cross Z2 one-form symmetry for psi prime. And it's this emergent one-form symmetry which is spontaneously broken away from the fixed points. So this is in fact a property of the phase, that there's some spontaneously broken one-form symmetry. Intuitively, modular tensor categories tell you about the possible generalized one-form symmetries that a system can exhibit. The corresponding topological order is the phase in which that is spontaneously broken. Next, I'd like to move on to mixed-state topological orders and repeat the same story. But before I do that, are there any questions about this perspective?
I personally didn't get fully the point why you talk about, but I know that many people do, so it's completely my sloppiness here. But why you talk about broken symmetry? I mean, maybe I didn't get the relation. It's a naive question, but you asked me for asking naive questions. So.
Oh, no, yeah, thank you. Yeah, it's good. So why am I talking about spontaneously broken symmetries?
Yes.
It's because I'll use that same technology to understand the classification of mixed-state topological orders. So to classify mixed state topological orders, we'll look at spontaneously broken symmetries. But it turns out for mixed states, there's an additional possibility which will lead to intrinsically mixed topological phases of matter. And I think it's quite natural to phrase in terms of spontaneous symmetry breaking.
So actually, maybe the question was, I think I would appreciate a refresher on that one too. It was what it means to spontaneously break a symmetry in this context.
Oh, it's precisely this condition that the connected correlator is non-vanishing in the separation of I and J. It goes to a constant. That's what I mean by it spontaneously breaks this one-form symmetry. It's the usual story of, in an icing model in one dimension. I can look at the connected correlator of ZZ operators, and that expectation value is 1, regardless of how far apart I take ZI and ZJ.
Right, and if I try to think of the usual picture I had of spontaneous symmetry breaking, but that's been a while ago, is that you have like a ground space that is degenerate and that has a symmetry, and somehow the ground state picks one direction or one kind of one configuration. And I guess this is the order parameter that tells you that you've actually picked one configuration as opposed to other configurations that would also be in the ground space. Is that the way I should think about it?
Right. So there are similarities there. The icing model is somewhat special because there is a symmetry preserving ground state, and there are ground states that don't preserve the symmetry. For the toric code, there is no symmetry preserving ground state. And what we find is there are ground states that they just don't preserve the symmetry. You can't be simultaneously a +1 eigenvector under those non-commuting operators.
Yeah, thanks.
But yeah, the way to say it is this connected correlator is non-vanishing. You pick up some long-range correlations in the ground state subspace.
Hi, I also have one question. So do you also have like topological order in 1+1 models, or is it like only when you go to 2+1 that you get a topological order?
Yeah, so this talk will focus on 2+1 dimensions. For bosonic systems, I would say confidently that there is no topological order in 1+1 dimensions. There is spontaneous symmetry breaking, of course, but that's spontaneously breaking a symmetry that acts on the full system instead of on these loops.
Maybe one last question to this spontaneously breaking the symmetry. I think the confusion may also arise because in the, like, if you have a zero form symmetry and you break it, you also can have a unbroken phase. Right, so the ferromagnet and the paramagnet. So, but here there is no unbroken phase, is there?
That's right, and it's precisely because these string operators don't commute with one another. Okay. So, yeah, I can't simultaneously diagonalize them. There isn't a state that's going to be an eigenstate of both of these at the same time.
Thanks.
Yeah, okay, great, thank you. Let's move on now to mixed states. We have to answer the same questions. Which mixed states should we consider? What equivalence relation should we oppose? Once we have those, what's the classification? Is there some way to understand this in terms of symmetries? There's one concept that I'll need to introduce to discuss which states and equivalence relation, and that's this idea of a quasi-local quantum channel, which will replace a quasi-local quantum circuit, which was used for pure state topological orders. Quantum channels in general are maps that take mixed states to mixed states. So here I have some mixed state rho and it's being mapped to n of rho. Any quasi-local quantum channel can be expressed in 3 steps. So here I've shown graphically the state rho. This is the mixed state rho. If this graphical notation is unclear to you, don't worry, I'll write it out explicitly below the diagram. So the first allowed step is to add ancilla. That's what I've represented here with the black dots. These are in a product state. So this is the product state. It's just a tensor product of 0 states in some region A. Second, we can apply a quasi-local quantum circuit. This is the quasi-locality of quasi-local quantum channels. So I've conjugated here the state tensored with the ancilla by a unitary U. And finally, we're allowed to trace out the ancilla. What does this mean intuitively? Well, intuitively, adding ancilla is like introducing environment in the system. Applying a quasi-local quantum channel is like allowing the system to interact with the environment for a finite amount of time through local interactions. And finally, tracing out the ancilla is like removing the environment. And in general, we'll be left with a mixed state. So which states should we consider? We're going to consider mixed states which arise from, or which can be constructed by applying a quasi-local quantum channel to the ground state of a gapped local Hamiltonian. I would say this is a very physically reasonable class of states to consider. Maybe you prepared a ground state of a gapped local Hamiltonian, or you're in the process of preparing it, and there's some noise. That would fit within this class of states. This class of states is still too large. It includes things that are spontaneous symmetry breaking in the usual sense. They break a zero-form symmetry or symmetry that acts everywhere, so we'll rule those out. We'll say that we're only interested in mixed states with short-range correlations. For any local operators, OI and OJ, this connected correlator vanishes sufficiently fast in the separation between I and J. This is the class of mixed states that we'll consider. They can be constructed from ground states of gapped local Hamiltonians via interacting with the environment for a short amount of time. We'll say two mixed state, yeah.
Is it guaranteed that the resulting row will be also some steady state of some gapped Lindbladian or so? Like because it's in pure state topological order, it's all about gapped Hamiltonians with respectively their ground states, and you can kind of interchange the pictures as you like. So I'm wondering if the similar story is true in mixed states.
Yeah, so maybe you want a Lindbladian that's local, and maybe by steady state you want some stability as well, something like this. Then the answer is probably no. I don't think that's true of the toric code, or at least we don't know Lindbladian whose steady state is just the 2D toric code and is stable. But in 4 dimensions, then the answer is probably yes. This is a different perspective that's been taken by Sarang Gopalakrishnan, Kurt von Kaiserlink, and Tibor.
One more quick question. So how does this simulating of the interaction with the environment using the single auxiliary qubits different from, say, you solve the Lindbladian dynamics directly?
So there are examples of quasi-local quantum channels that can't be implemented by finite time evolution by a local Lindbladian. And we'll see an example of that momentarily. Our first example, this X-decohered toric code, is such a situation. But otherwise, I suspect if you allow for infinite Lindbladian evolution, something like this, then you can relate the two. But intuitively, yes, you should think of this as finite time evolution by a local Lindbladian, with some exceptions.
Sorry, but maybe can you say like when would that not be the case? Like when would that fail?
Yeah, it fails when this quasi-local quantum channel is degenerate. So you can run into a situation where it maps the same state, it maps different states to the same mixed state. And that doesn't happen for Lindbladian evolution. So as a quick example, let me scroll to some backup slides here. And this also will emphasize why two-way connectivity is important. So here's a quasi-local quantum channel, which is highly, highly, highly degenerate. And it cannot be implemented by a finite time evolution by a local Lindbladian. So what I'll do is I'll start with any mixed state. You choose your favorite mixed state. I'll add ancilla in a product state. I'll apply a finite depth circuit that swaps the ancilla in the mixed state. This can be done with a local circuit, a finite depth quantum circuit. Then I'll trace out the ancillary degrees of freedom. Trace of rho is 1. So it maps any density matrix to a product state. That's highly degenerate. Okay, we have a class of states. Was there another question?
No, it's just someone said that makes sense.
Okay, good. Yeah, we have a class. Good. Yeah, I'm glad. At least somebody's getting it. Yeah, so we have a class of we have a set of states that we'll consider. Now we'll impose an equivalence relation. So let's say two mixed states, rho 1 and rho 2, are equivalent or belong to the same mixed state topological order if there exists a pair of quasi-local quantum channels such that one maps rho 1 to rho 2 and the other maps rho 2 to rho 1. In other words, we have two-way connectivity by quasi-local quantum channels. Two-way connectivity is important, as I just showed, because any mixed state can be mapped to a product state with a quasi-local quantum channel. What's more non-trivial is, well, can that state be prepared from a product state with a quasi-local quantum channel? This equivalence relation, again, partitions a space into equivalence classes, and we designate the equivalence class with the product state as the trivial mixed state topological order. All others are non-trivial mixed state topological orders. And as I mentioned earlier, I'd like to understand the space of possible mixed state topological orders by considering the spontaneously broken symmetries. That means that I'll need to say a few words about the symmetries of mixed states. Mixed states have two possibilities for their symmetries. The first is a weak symmetry. This is the usual notion of how an operator transforms under the symmetry just by conjugation. We say rho has a weak symmetry represented by W if conjugation by W leaves the state rho invariant. Intuitively, what does a weak symmetry mean? Well, I can express rho as a mixture of pure states. This is just diagonalizing rho. And what a weak symmetry tells us is that each state in this pure state decomposition of rho is an eigenstate of the symmetry with some eigenvalue e to the I phi I, which may depend on I. This might arise, for example, if you have a symmetric system. It's allowed to interact with the environment for a finite amount of time, and the environment exchanges charges with your system. So it changes the eigenvalue of these pure states. But the symmetry is preserved on the system environment in total. The other notion of symmetry that's possible for mixed states is that of a strong symmetry. We say a mixed state rho has a strong symmetry if the left action by the symmetry operator is the same as just multiplying by a phase. Intuitively, what does this mean? It means that in a pure state decomposition of rho, each of the pure states will be an eigenvalue of the symmetry, will be an eigenvector of the symmetry operator with an eigenvalue e to the I phi, which is independent of the index I. This is like a situation where you allow the system to interact with the environment for a finite amount of time, but the environment preserves the symmetry on your system. It doesn't transfer any charges. So there are two notions of symmetry. Now we can ask, armed with this understanding, what's the classification of mixed state topological orders? Is there a sense in which the symmetry is the strong generalized one-form symmetries are spontaneously broken? And we'll start by considering the toric code and analyzing a transition that takes us from the toric code to the trivial phase by adding noise. This is the example of the X-decohered toric code. But let me just see if there are any questions before I dive into that.
Yeah, I have a question. Maybe could you, of course, it would maybe make the analysis much more tedious, but could you in principle also start with any other pure state topological order and investigate similar transitions? So does any pure state topological order give rise to a different tile in your in your diagram on the right?
The answer is yes. I don't have a simple way of stating that, but the answer is yes. Essentially, you can use the fact that the answer is yes. The well, I'll use the words. The modular part of the one-form symmetries is a topological invariant. This we can prove.
Okay,
just a tiny question, like on the on your definition of the weak symmetry, what do you end up working with? Do you end up working with a very left definition, or do you end up working with a very right definition?
Sorry, I think I missed some keywords there. Can you repeat that? Sorry.
I'm wondering if you work with the very left characterization, or the one on the right side, because on the left side, in principle, you could also still permute the states and the degenerate eigensectors of the state, right? Like if you have multiple eigenstates with the same occurring with the same pi, those can be permuted by the symmetry operator, which
yes,
is conflict with the pure state thing on the right.
They're actually equivalent, so I can because this on the left shows that W and rho they commute, so they can be simultaneously diagonalized. And I can write this as a mixture of pure states where they're all just eigenvectors of W.
Okay, cool. Thanks.
Yeah, thank you.
Good. That doesn't matter.
All right, let's add some noise. The noise that we'll add to the Tora code is implemented by a bit flip channel. The bit flip channel, all it does is with some probability p, it'll flip the spin. It'll apply a Pauli X operator. With probability 1 minus p, it does nothing. It leaves rho the same. And with probability p, we conjugate rho by the Pauli X operator. Next, we'll define a global bit flip channel. This is just like applying the bit flip channel to every site or every edge in the Tora code. This can certainly be implemented with a quasi-local quantum channel. Let's consider the extremes of this global bit flip channel. If p is equal to 0, then we don't flip any of the bits. On the other hand, the maximum strength channel occurs when p is equal to 1/2. Then for every edge, there's a 1/2 probability that you'll flip the spin. This means that any density matrix under this maximum strength channel is like conjugating by all possible combinations of Pauli X operators. So let's apply these channels to the Tora code. When p equals 0, we just have the usual pure state Tora code. When p equals 1/2, we'll have what I'll call the X decohered Tora code. We're conjugating this Tora code state and adding up all possible applications of Pauli X operators. At the far left point, at p equals 0, we've already seen that this spontaneously breaks a strong Z2 cross Z2 one-form symmetry. On the other hand, at p equals 1/2, we have an explicitly broken strong Z2 one-form symmetry. How do we see that? Well, let me write the X decohered Tora code state explicitly. Here it is. This state, since it's all possible applications of Pauli X conjugations by Pauli X operators, it's invariant under conjugation by a Pauli X operator. That means that the strings in the ket have to match the string configurations in the bra. Since we're starting with the Tora code, it only has closed string configurations. So we end up with a mixture of string configurations where the configuration in the ket has to match the configuration in the bra. We've explicitly broken the strong Z2 one-form symmetry, which corresponds to adding a loop of blue string. Because if we add a loop of blue string, if we act on the left of this state with a plaquette operator, what it will do is it'll change the configuration in the ket and leave the bra invariant. So that'll take us to a different state. So we've explicitly broken this strong Z2 one-form symmetry. So you might expect that there has to be some phase transition that occurs within this phase diagram. And in fact, there is a phase transition. This occurs at a critical error rate of 0.109. And we go from a non-trivial phase, which corresponds to the Tora code phase, to a trivial phase. So it turns out all the states to the right, including the X decohered Tora code, are two-way connected to a product state. We can construct them by a quasi-local quantum channel from the product state and vice versa. What happens within this non-trivial phase? Well, similar to the pure state case, we can interpret this as spontaneously breaking an emergent one-form symmetry. In interest of time, let me not go into this explicitly, but there is a notion of emergent symmetries for mixed states. And at the end of the day, the point is there's spontaneous symmetry breaking of the emergent Z2 cross Z2 one-form symmetry within this phase. And on the other side of the diagram, we still have a Z2 one-form symmetry, which is the X one-form symmetry. And we can ask, well, what happens to that one-form symmetry? And we'll address that in a moment. But first, I'd like to mention that this Z2 cross Z2 one-form symmetry is anomalous, which all that says is that there's an obstruction to constructing these states from product state. This Z2 one-form symmetry, on the other hand, is anomaly-free. So there's no obstruction from constructing this state from a product state. And in fact, that's possible. But let's think more about what happens to this Z2 one-form symmetry that's anomaly-free. It cannot spontaneously break the symmetry. It cannot be that that Z2 one-form symmetry is spontaneously broken in the usual sense, because that would say that we can create long-range correlations from a product state by applying a quasi-local quantum channel. And that violates some Lieb-Robinson bounds for quasi-local quantum channels. And we can see that indeed, the connected correlator vanishes sufficiently fast. So there is no spontaneous symmetry breaking. Let's see that explicitly. Again, we can take this order parameter, or at least propose as an order parameter, a Z string operator. This is still charged under one of the remaining Z2 symmetry that's generated just by a product of Pauli X operators along the x-axis. But what happens when we try and compute the connected correlator? Well, here's the connected correlator for the state for the X decohered toric code. We're applying string operators to the left of the decohered toric code. What that does is it changes the configuration of the strings in the ket relative to the configuration of the strings in the bra. So we take the trace, we end up with 0. So the connected correlator vanishes sufficiently fast. But there is something non-trivial happening here, which is special for mixed state phases of matter. What we're actually seeing here is that there's a spontaneous symmetry breaking from a strong symmetry to a weak symmetry. This cannot happen for pure states. There's no notion of strong and weak symmetry for pure states in the same sense. But here we have a strong symmetry spontaneously breaking to a weak symmetry. And the way to see that is to generalize this notion of a connected correlator. We see that if we apply the string operators to one side of rho, then we're going to end up with the trace of 0. But what happens if we apply them to both sides? Well, if we apply them to both sides, then you just use the cyclicity of the trace, and you get 1. But what if we apply them to both sides and insert a second copy of rho? This defines a sort of Renyi-2 connected correlator. So that's exactly what I've done here. I'm taking the trace of the order parameters conjugating rho with a second factor of rho. So this is quadratic in rho. This Renyi-2 connected correlator is non-vanishing in the separation between I and J. In fact, it tends to a constant in the separation of I and J. How do we see that? Well, in the leftmost term here, we're conjugating the X decohered toric code by these string operators. That means we create those string configurations in both the ket and the bra. Here we've gone from an even number of strings in the X decohered toric code wrapped around the y-axis to, again, an even number of strings wrapped around the y-axis. So the trace here will just be the trace of the X decohered toric code squared. And over here, we've changed the parity of strings, so these will be 0. So this is 1 once we divide by the purity of the X decohered toric code, and these are 0. So at the end of the day, we find that this Renyi-2 connected correlator is constant in the separation of I and J. And this is an indication that there is strong to weak spontaneous symmetry breaking. Yeah, that question?
Cool. But I was wondering, what's the meaning of this Renyi-2 connected correlator? Because at the end, it's like a overlap between mixed states. Since you're applying unitaries, you could have quantify the same thing that I think that you're quantifying with some trace distance between. I don't know. I mean, I don't know what's the meaning of that. So that's
yeah, absolutely. Yeah, I could have used fidelity instead. I conjugate the operator and consider the overlap with an operator that's not conjugated. So yeah, ultimately you'd want to define this in terms of fidelities. Okay. But just for the simplicity of exposition, I've used here a Renyi-2 connected correlator.
Okay, but this is no longer the meaning of correlations, or it has a meaning of correlations in some sense? I mean,
it's like there are correlations in a double of the system.
okay.
You know, I can take my density matrix, I can turn around the bra so that I have two cats. And then it's like saying that there are long-range correlations in that pure state. Intuitively, I think.
Are you referring to the Choi isomorphism, something like that? Or?
Yeah,
okay.
yeah, vectorization, the Choi isomorphism.
Yeah.
That's right.
But that would be true even for a maximally mixed state, right? Like the vectorization of a mixed state is a Bell state. And that seems to be like a meaningless correlator in that context.
That's true. This will also vanish in that context. So it's not a if and only if statement. It's not a statement that if the double state has long range correlations, then the Renyi-2 connected correlator of the mixed state is non-vanishing. You see what I'm saying?
I think so.
Yeah, maybe I find it difficult to reason about this Renyi-2 correlator. The point is that this is an indication that there's strong to weak spontaneous symmetry breaking. But what does this mean? So maybe a more intuitive picture is to do the following. We can just consider the states, the X decohered toric code and the X decohered toric code conjugated by these Z string operators. These two mixed states are locally indistinguishable. You should think of these as like I have some one-dimensional system that spontaneously breaks a Z2 symmetry. These are two different ground states in a sense. They're locally indistinguishable, replaces the notion of a ground state. These two states both have a strong symmetry generated by this string of X operators. So if I apply this to the left of the X decohered toric code, I get the X decohered toric code back. If I apply this to the state conjugated by Z, since there are an odd number of strings wrapped around the torus, then I'll get a -1 sign. So there's still a strong one-form symmetry. But what's sort of indicative of spontaneous symmetry breaking is that within the space of locally indistinguishable states, you can ask, well, is there still a strong one-form symmetry? And the answer is no. I can take a mixture of these states, and that mixture will no longer have a strong symmetry, but it does have a weak symmetry. So any mixture of states within the space of locally indistinguishable states will have a weak symmetry, but it will not have a strong symmetry. This is like saying, well, yes, there are symmetry preserving ground states of a 1D Ising model, but if I take a sum of them, if I take a coherent superposition of them, I'll end up with a state that breaks the symmetry. And that breaks it down to nothing. Here, instead of breaking it down to nothing, it breaks it down to a weak symmetry. That's the intuitive explanation for why you should call this strong to weak spontaneous symmetry breaking.
Now, in terms of the phase that you associate to that state above the threshold of this applying this noise parameter, it doesn't actually matter as far as you said, because you you still say it's in the trivial phase. I can still prepare it from the product state. So somehow you like local quasi-local quantum channels can have this, can create emergent, what was it, weak one-form symmetries or strong? But like, is there some physical meaning to that, or is it just a coincidence that started
so this
a state?
Yeah, this example is kind of trivial. You're right. What this says is that strong to weak spontaneous symmetry breaking can be prepared, can be constructed, can be built from a product state with a quasi-local quantum channel. So strong to weak spontaneous symmetry breaking does not define a phase per se, but we can add an additional ingredient. What if that strong symmetry is anomalous? Then it would be a phase that is distinct to mixed state topologicals, phases of matter. So that's what I'll do next here. I'll show an example which is strong to weak spontaneous symmetry breaking, and the symmetry is anomalous, unlike this case where the symmetry was anomaly free. So it will still belong to a non-trivial phase.
So you, yeah, so you mod out the modular part kind of, and then you see what is left, and if this is, does it make sense?
Not quite. So the strong to weak spontaneous symmetry breaking happens when there is a premodular part.
Yeah, okay.
The question is whether that premodular part is anomaly free or not. If it's anomaly free, then there's no obstruction to constructing it from a product state. But if it is anomalous and premodular, then you have something interesting.
Cool. Yeah.
What does it mean, anomalous or anomaly free? But yeah.
Yeah, that's a good question. The way I've defined it is just whether it could be prepared from a product state, but that's just a cop-out. What do I mean by anomalous or anomaly free? It means that if you have a one-form symmetry that's supported on these one-dimensional submanifolds, at least in 2+1 dimensions. Now, what you can do is you can cut open this symmetry operator, and at the endpoint, it'll create excitations. It'll create anyons. We say the symmetry is anomalous if when you cut open these string operators, they create anyons with non-trivial braiding relations or non-trivial statistics.
Okay. So
in the case of the toric code, it's anomalous because you can truncate it. In one case, you get E anyons. In the other case, you get M anyons. These have non-trivial braiding relations. There's a mixed anomaly. We'll see an example where when you cut it open, what you get are emergent fermions. You get EM anyons of the toric code. These have trivial braiding relations, but they have non-trivial exchange statistics. So we'd still say it's anomalous. In this case, the Z2 one-form symmetry is only generated by these products of Pauli X operators. So if you cut it open, you get only the M anion. M braids trivially with itself. M also has trivial exchange statistics, so it's anomaly free. You can write down a product state that has this same symmetry. Okay. So you've seen now that for mixed state topological orders, there's an additional possibility. Not only do the phases correspond to spontaneously breaking a strong generalized one-form symmetry, we can now have that the symmetry is broken from a strong symmetry to a weak symmetry. To generalize this and find a non-trivial example, what we're going to do is discuss a different perspective on this X-decoherent toric code. It looks like I'm running out of time, so I'll make this sort of brief. But here's a different perspective on the X-decoherent toric code. We can understand it in terms of incoherently proliferating anyons. So again, this X-decoherent toric code is applying the maximal bit flip channel to the toric code state. This looks like all possible application conjugations by Pauli X operators. What do Pauli X operators do in the toric code? What they do is they create M excitations. They create violations of the plaquette term. So one way to think of this X-decoherent toric code is we're conjugating by all possible products of Pauli X operators. This is creating all possible configurations of plaquette violations, all possible configurations of M anyons. So what I have here is a sum over M configurations. And we'll say that we've incoherently proliferated the M anyons. I'll draw, yeah.
You also get the non-trivial loop, though.
You also get the non-trivial,
so,
right?
Is that just implicitly included in the sum, or how would you understand it? Because there are two orthogonal states which both have no M anion in it. That's
I think yeah, that's a good question. That's right. Maybe this notation is insufficient. Maybe you also need something global to say here as well. Yeah, that's a good point. Okay, on a sphere, this is what you get. This is what you get on a sphere. Yeah. All right, we see now that we can incoherently proliferate M anyons. There are other anyons in the toric code. We can incoherently proliferate an E anion, a violation of vertex term. That's kind of boring. It produces the same thing as incoherently proliferating M anyons just because of an EM duality. Another option is to incoherently proliferate an EM anion. EM is distinct from E and M in that EM is a fermion. This comes from ultimately the fact that E and M have non-trivial braiding relations with one another. So there's a potential to incoherently proliferate an emergent fermion. Before doing that, let me say a few words to distinguish this from coherently proliferating anyons or condensation of anyons. A coherent proliferation of M anyons would be a superposition of M configurations, with the key property that applying the pair creation operator and X operator to the state leaves the state invariant. For incoherent proliferation, we require something weaker. We only require that the state is invariant under conjugation by X operators. So we just have a incoherent proliferation of M, a classical mixture, a probability distribution of M configurations instead of a superposition of M configurations. Now we can ask, is this possible for the case of incoherently proliferating fermions? Coherent proliferation, condensation of fermions, is not possible. There's an obstruction to doing this. The problem is that we cannot find pair creation operators that are all mutually commuting. That means that this condition, applying the pair creation operator to the toric code state, to this condensed state gives you the state back, is not possible. And that's precisely because the fermions have non-trivial exchange statistics. On the other hand, incoherent proliferation is possible. We just require this weaker condition. Conjugation by the pair creation operators leaves the state invariant. And now there's no obstruction to finding such a state. And we can do that explicitly. In interest of time, I'll say this. Maybe I'll just jump to the punchline. The point is you can define some noise. What this noise does, it creates fermions. Again, there will be a phase diagram. At p equals 0, we haven't created any fermions. The toric code at p equals 1/2, we have created, we've proliferated fermions. It turns out there's a phase transition. It again happens at this point, 109 error rate. And distinct from the X decohered toric code, the maximally decohered state is in a non-trivial phase. And what happens here is that there's an emergent Z2 one-form symmetry, but it's anomalous. This is the one-form symmetry corresponding to a string operator for an EM anion. It's a product of poly X and Z operators. And since it's a product of poly X and Z operators, when you cut this open, it could have non-trivial exchange statistics, making this anomalous. So here we actually have a spontaneously broken, this is again, I should have written it here, but this is a strong to weak spontaneous symmetry breaking of an anomalous symmetry. So this is an intrinsically mixed topological order. We also have a construction that's far more general if you give us a generalized one-form symmetry of your choice. We have a way of building a mixed state that exhibits that that spontaneously breaks that generalized one-form symmetry. And at the end of the day, we have conjectured that the mixed state topological orders are classified by pre-modular tensor categories. These are more general than modular tensor categories in that they allow for anyons that have trivial braiding relations with one another, or anyons that are transparent. These intuitively capture all allowed generalized one-form symmetries in 2 dimensions. And from the symmetry perspective, we spontaneously break one of these symmetries corresponding to a pre-modular tensor category. And now what makes for intrinsically mixed topological orders are those that have a strong to weak spontaneous symmetry breaking. I'll wrap things up. We've conjectured that mixed state topological orders are classified by pre-modular tensor categories, this abstract mathematical data, which I didn't define concretely. And what you didn't see is a construction of a mixed state that spontaneously breaks this input one-form symmetry corresponding to the pre-modular tensor category. One way of constructing mixed states was to incoherently proliferate anyons. There's a second notion of constructing intrinsically mixed states by classically gauging a symmetry instead of quantum gauging a symmetry. I won't go into this now in interest of time. And let me just conclude by listing some open questions. First of all, for pure state topological orders, we know that if the anion theories are distinct, if they exhibit different, if they spontaneously break different symmetries, then they belong to a different phase. The equivalent statement is not yet proven for mixed state topological orders. If they correspond to a distinct set of anions, if they correspond to a distinct premodular tensor category, does that mean that they belong to distinct mixed state phases? We aren't sure yet. Second, topological quantum field theories have been very valuable for understanding the classification of pure state topological orders. You could ask, well, is there a similar notion for mixed states? There's a very short paper, it's 1.5 pages, that introduces the idea of mixed state topological quantum field theories, but there's a lot more that can be elaborated on here.
I would say.
Yeah, so we're talking about the classification of mixed state topological orders. Another important question is their characterization. If you hand me a mixed state, can I tell you which topological phase it belongs to? For pure states, one productive route has been to study the topological entanglement entropy. In this case, you might want to use a mixed state measure of entanglement, such as the negativity, and define a sort of topological entanglement negativity for characterizing mixed state topological orders. Lastly, there has been an incredible amount of progress in understanding pure state topological orders at the level of the state, instead of invoking any parent Hamiltonian. This goes by the name of the entanglement bootstrap program. You impose some conditions on the entanglement properties of the state, and you can drive the classification of pure state topological orders. Now, similarly, you can ask, is there a Hamiltonian-free way to define mixed state topological orders and a generalization of entanglement bootstrap to mixed states? Okay, sorry for the expedited conclusion. I did promise that, so I'm glad I followed through, but I'll end here. Thank you for your attention.
Yeah, thanks a lot. Is there any questions? Yeah, go ahead.
On a more technical level, I'm super curious on how you catch the phase transition between the the toric code phase, between the phases. I mean, the phase transition you showed us, how did you capture that?
So this is, are you talking about the X decoherent toric code?
Yes.
You're talking about this phase diagram.
0.109.
Yeah, exactly.
Yeah,
I mean,
this
not that I care about the point, but I care about the end of, speculation.
That's a great question, and there is a fantastic paper to address that. It's here by Reihua Fan, Yimu Bao, Ehud Altman, and Ashwin Vishwanath, where they actually study 3 different quantities across this phase transition. They do study a topological entanglement negativity. They study a coherent information across this transition, and there's a third relative entropy or something like this across the phase transition. And what they find is that what they're able to study is like Renyi versions of these. And the Renyi versions give you critical points that are upper bounds. So they'll give you critical thresholds that are up here. And they conjecture that if you take the Renyi index to 1, you recover this critical point that corresponds to the transition for the mixed state topological orders.
Okay.
So there's a wonderful paper. The title starts with diagnostics of mixed state topological orders. So some diagnostics, something like this.
Okay. But is this phase study numerical, I guess? It's a numerical study.
For some of the simpler Renyi entanglement quantities, they were able to come up with analytical solutions, analytic solutions. But yeah, otherwise it's numeric. This 10.9 is numerics.
Thank you.
I have a question. Yes, go ahead.
Oh, okay, thank you. So I have a question. So you brought it up in your last slide with respect to the universality of the decoherent topological orders. I was a little bit reminded of the classification of disordered topological insulators, where what you can do is, so it's like an SPT. You can add some sort of disorder which breaks the symmetry, but then you do a disorder average and preserves it on average. Now, a question that you could ask is, well, is your disordered system in the same phase as the original system? And for some cases, the answer is yes, and for other cases, it's not. For instance, what could happen as a result of disorder averaging is that you would turn on Anderson localization, and then your system is in a distinctly different phase. In this setup, I understand that you're not dealing with disorder of the type that you would in, let's say, something like an electron gas, but you're instead dealing with some form of decoherence. But is there any related statement of universality that you could make, for instance, by leveraging a field theory or something like that?
By leveraging a field theory. So maybe I should first say that this work was ultimately inspired by the work on disordered topological insulators. People started thinking about, well, what other SPT phases can we define in this average symmetry setting? And there they realized, okay, you can have some anomaly that's mixed between weak symmetries and strong symmetries. There's some interplay between weak and strong symmetries, which gives you intrinsically mixed SPT phases. This is the generalization of that story to topological orders, where now you have some strong possibility of strong to weak spontaneous symmetry breaking. But now your question turned to, is there a field theoretic interpretation of the classification? And that I don't know. This is the second question here about finding a notion of mixed state topological quantum field theories.
And perhaps a related note, so you conjectured that all the decohered phases were classified by a premodular tensor category. Is there a set of conditions under which a premodular tensor category can be converted into a modular tensor category?
Yeah, so premodular just means that there's a possibility to, so what does modular mean? I'll think of a modular tensor category as just an anion theory. It defines some objects, those are your anions. They have fusion rules, braiding relations, they satisfy some consistency conditions. That's the information of a modular tensor category. Modular means that for any anion, there exists some other anion with which it braids non-trivially. Premodular means you can have a situation where there's an anion that has trivial braiding relations with itself and all other anions. So if the premodular anion theory has no transparent anions, then it's modular.
I see. Thank you.
Yeah.
Hey, thanks for the nice talk. I had a question, and I'm sorry if I missed it. I was curious about what happens if you take a pure state topological order and you start looking at it at finite temperature. Is there like some critical temperature up to which this is a quasi-local map or something like that? And can you say something about does this connect to robustness of topological order at finite temperature?
So that's a great question. In 2+1D, there's an argument by Matt Hastings that says that at any non-zero temperature, we lose the topological order. In the same sense, there's some quasi-local quantum circuit that maps back and forth to the product state. So yeah, at non-zero temperature, these all get washed away in 2+1 dimensions. But you can ask, well, is there something more non-trivial that happens in 3 dimensions? The answer is yes, or in 4 dimensions. But yeah, any non-zero temperature, this all gets washed away. So okay, I motivated this story by saying, yeah, experimentalists are dealing with all this noise and stuff. They're also dealing with non-zero temperature. So why isn't that a concern? Well, okay, what's the physical meaning of this? You maybe have some active error correction on top. You have some mechanism for cleaning up some of your errors. So you stop the errors from spreading too much. And then these are the different fixed points of your error corrections.
Yeah, okay, sorry, now I got confused because I thought that you had in because you were looking at the equivalence class with respect to these quasi-local errors, even in 2+1 dimensions. But you said, but like if I have, well, say if I have the X decohere toward code at just very small values of the decohering, those are with respect to this, to these open system, these channel maps, quasi-local maps, they're in a different topological state. They're in a topological phase than the product state, right? So doesn't that tell me that they have to be robust in a way, according to this definition?
They're robust in a way. They're robust to just a small amount of bit flip noise, but they aren't robust to non-zero temperatures. Yeah, that's more extreme.
Okay. Okay. I see. Yeah, thanks.
Yeah. And your question of, well, can you model going to a non-zero temperature with applying a quasi-local quantum channel? Possibly. But the question isn't whether that can be implemented with a quasi-local channel. It's again about two-way connectivity. So you might be able to heat up the system easily, but going back's the hard part.
Mm-hmm.
I also have more time. I have a question on the classification in the end. So just a clarifying one on the two examples where you decohered the toric code differently. In one case, you ended up in a trivial phase that connected to the trivial one, but you still had a one-form symmetry. And you argued that also the product state has, you can write down a product state that has this one-form symmetry. From what you said earlier, I would have expected that the existence of a one-form symmetry or the one-form symmetry that your state exhibits tells you the is the invariant classifying the phase. So, and I would have expected the product state phase to just be classified by the trivial, like the trivial instance of whatever classification. So the trivial pre-modular tensor category with just the vacuum and nothing else. But now you write down the product state that has a non-trivial one-form symmetry. So would you consider it to be classified by like all pre-modular tensor categories that are only bosonic, or what's the, how do you get out of this, that you can always add like fully transparent bosons and you don't change anything?
This is an excellent point, and really I should be more careful in claiming that the classification is the same as pre-modular tensor categories, but because what you're saying is I can always tensor in a factor that's just a bunch of trivial bosons, and those are anomaly free, and that's true. So you really have to mod out by products of trivial bosons, because you can realize those one-form symmetries in, say, a product state. There's no obstruction, and that's true for pure state topological orders as well. The product state has that same Z2 one-form symmetry. But I can put this on qubits and realize more complicated one-form symmetries that only contain bosons. So you do need to mod out by factors of transparent bosons.
Okay, thanks. Cool.
Yeah, that's a good point.
Okay. If there are no further questions, I would thank Tyler again. Thanks.